We've watched AI agents get pretty good at navigating the web, clicking buttons, filling out forms, even buying things.
Yeah, the progress there has been pretty remarkable.
But then you ask that same agent to, say, open Microsoft Word, format a specific paragraph using the ribbon, and then maybe drop in a custom Excel chart.
And it all just
Yeah,
falls apart. It's a completely different ballgame.
exactly. So today on AI Peer Review, we're diving into what feels like the real frontier for these autonomous agents, the desktop. Specifically, computer-using agents, or CUAs.
And we're basing this on a really fascinating, incredibly detailed paper. It introduces something called GUI-360 degrees.
Okay.
It's this huge new data set and benchmark suite. And honestly, it seems like the first resource that genuinely captures the chaos and complexity of using professional Windows apps. Think Word, Excel, PowerPoint.
Right, the stuff people actually use for work every day. So our mission today is to unpack why the desktop environment is just so much harder than, say, web or mobile environments.
And as we'll see, the data points to this critical bottleneck. It's actually quite surprising. The agents often figure out what they need to do.
Uh-huh.
But they consistently fail at figuring out where on the screen to do it. The grounding is the issue.
Wow, okay. So it's a targeting problem.
Precisely. And the level of detail in this data set is, well, unprecedented for this domain. We're talking over 1.2 million action steps.
1.2 million.
Yeah, across thousands of real task trajectories. And they captured everything. Full-res screenshots, the agent's intermediate reasoning or thoughts, and crucially, all the accessibility metadata that defines the UI elements.
Okay, let's unpack this. What makes the desktop environment so much harder than what we've seen before? If a vision model can spot a cat in a photo, why is finding the merge cells button in Excel such a hurdle?
Well, fundamentally, it boils down to structure, or rather the lack of it. Desktop apps are just messy.
Messy how?
You've got these high-resolution screens, often with multiple windows overlapping in arbitrary ways. The widgets themselves are incredibly varied, heterogeneous. They don't follow the nice, predictable, standardized HTML structures that web agents can latch onto.
Ah, okay. No DOM equivalent, really.
Exactly. And maybe even worse, these applications often lack good, consistent accessibility metadata. That's the underlying map of the UI. Without it, or if it's unreliable, visually grounding instructions becomes exponentially harder than on the web.
So the limitation in previous work was partly the data itself. It just wasn't capturing this real-world desktop complexity.
That's a big part of it. The researchers behind GUI 360 degrees point out 3 specific gaps they wanted to fill.
Okay, what were they?
First, just a scarcity of real-world task collections. Before this, most data sets used tasks that were either, handcrafted by researchers.
Which might be too simple or not representative.
Right. Or they were synthesized by LLMs, which again, might not capture the authentic, sometimes awkward ways real users try to get things done.
Makes sense. What's the second gap?
The lack of automated pipelines to collect these rich, multimodal trajectories at scale. I mean, just imagine manually logging 1.2 million clicks, types, drags, and the screen state and the metadata for each step is just not feasible.
No way. And the third?
We didn't have a single unified benchmark that could jointly evaluate all the core capabilities a CUA needs. You need to test grounding, understanding the screen layout, and predicting the next action, all together.
Right. Let's clarify those core capabilities then. What are the essential tasks a CUA needs to nail?
You can think of it like the steps a person takes. First up is GUI grounding. So if I give an instruction like open the document settings, the agent needs to map that language precisely to the right spot on the screen. Is it a gear icon? A menu item? It has to predict the exact coordinates or the specific UI element ID.
Okay, find the target. Then what?
Then you need to understand the whole playing field. That's screen parsing.
Parsing. So like identifying everything you could interact with?
Exactly. Given just a screenshot, the model has to list out all the interactable UI elements, buttons, text boxes, drop-downs, along with their names and their locations, their bounding boxes. If the agent can't see what's clickable or usable, it's stucka.
Makes sense. Grounding finds a thing, parsing finds everything, and the final piece.
That's the ultimate goal. Action prediction. Given where you are, what you see, and what you're trying to achieve, predict the very next executable action. That could be a low-level thing like click X42, Y41, button left, or typing text or dragging something.
But I saw in the paper they make a point about the type of actions. It's not just clicks and types, right? They use this hybrid GUI plus API action space.
Yes, and this is really practical. It reflects how you'd want a modern, efficient CUA to work.
How so?
Well, think about changing text color in Word. A naive agent might click through 3-ribbon menus and navigate dropdowns. Very slow, very brittle.
Yeah, painful to watch.
Yeah, right. A more efficient agent should ideally be able to use a higher-level, application-specific API call if one exists. Something direct like set font color, selection red. So this hybrid action space mixes those low-level GUI primitives click, type, drag with these more powerful app-specific API calls like set cell value in Excel or select text in Word. It aims for robustness and efficiency.
Okay, that hybrid approach makes a lot of sense. Now, generating this data set, 1.2 million steps automatically. That's a huge engineering feat itself. How do they pull that off without armies of humans, especially ensuring the tasks were actually realistic?
They tackled realism right at the start in the query acquisition phase. They went to where users actually get stuck and ask for help.
Like support forums.
Exactly. In-app help content, online Q&A sites and forums, and crucially, high-frequency search queries. Real problems people search for.
So they're literally training the AI on the things that generate the most help desk tickets or Google searches. That's smart.
It is. They mentioned pulling over 25,000 queries just for word from search logs alone. But obviously, you can't create a unique Word document setup for every single one of those queries.
Right, that wouldn't scale.
So that's where their efficiency trick comes in. Environment template construction. They designed a limited set of core environment templates. Only 66 in total, 30 for Word, 30 for Excel, 6 for PowerPoint.
Only 66, but they cover most cases.
Apparently, yes. They estimate these 66 templates collectively cover about 95% of the prototypical queries they gathered. It makes the environments consistent and manageable.
Okay, so you have realistic queries and standardized environments, but the search queries are often pretty vague, right? Like how to make text bold. How do you get a concrete task from that?
That's the next step, task instantiation. They use an LLM to translate that fuzzy natural language query into a specific executable instruction that makes sense within the chosen template.
So the LLM acts like a translator.
Exactly. It takes, how do I make text bold? And turns it into something like make the text hello world, bold in the current document, and set the font size to 14 point. Something concrete the agent can actually try to execute.
Got it. And then the trade agent takes over and actually performs the task.
Right. Trade agent is this orchestrated system they built. It runs the task and records everything for that trajectory. Not just the final screenshot, but the full-res screen capture at each step. The accessibility API data from Windows.
That structured UI data we mentioned earlier?
Yes, the UI automation data.
Yeah.
And it even logs the intermediate thoughts or reasoning traces from the agent trying to solve the task. It's incredibly rich data.
And this framework enabled a pretty clever collection strategy, didn't it? Something about 2 stages.
Yes, this was quite smart. They first ran the tasks using GPT-4o, which is very capable, but maybe, let's say, optimized for speed or cost.
Okay.
Any task query that GPT-4o failed to complete successfully was then automatically retried using the presumably stronger or more robust GPT 4.1 model.
Ah, so they used the premium model for the hard cases.
Exactly. And this significantly boosted their overall task completion rate up to about 26%. More importantly, it ensured the dataset wasn't just full of the easy wins, but also included successful trajectories for more difficult edge case tasks. It improves coverage and diversity.
Okay, so now we have this gold standard data set, the GUI 360 degrees benchmark. Time for the moment of truth. How did the current state-of-the-art models actually do when tested on this? Let's start with that fundamental task, GUI grounding, finding the target.
Well, the out-of-the-box results for generalist models were, frankly, quite poor.
Really? Even the big names?
Yes. General-purpose vision language models, think GPT-4o, GPT-4.1, they scored overall accuracies well below 12%.
12%? Wow.
Yeah. It tells you immediately that these powerful models, just used off the shelf, are really lacking when it comes to grounding language instructions to precise locations on a complex desktop UI.
But presumably training on this data helps. What about fine-tuning?
Oh, absolutely. Fine-tuning made a massive difference. Just doing domain-specific pre-training got performance over 50%.
Okay, that's a big jump already.
But then, supervised fine-tuning, or SFT, directly on the GUI 360 degrees training data. That pushed accuracy way up. Models like Qwen 2.57b reached over 82% accuracy on grounding.
82%, that's huge. So the data set itself is incredibly valuable for training. It clearly teaches the models something crucial about desktop UIs.
Definitely. Teaches them the specific visual patterns, the semantics of these dense, sometimes non-standard layouts.
Okay, that's a big win for grounding then. But hang on. If they can get grounding accuracy up to 82%, why are the overall action prediction results, which we'll get to, still relatively low? Something doesn't quite add up there.
That's a really sharp observation. And it points toward the difference between finding one specific target element correctly versus understanding the entire interactive landscape. To bridge that gap, let's quickly touch on the screen parsing results.
Right, the task of identifying all the clickable things on screen, building that full map.
Exactly. And this task turned out to be brutal for the general models. They used tough metrics like F1 score, precision, recall.
And how did the general VLMs do?
They basically failed. Their F1 scores maxed out around 0.128. They might be able to spot, one or two obvious buttons.
But they can't map out the whole complex interface of something like Excel.
Not even close. They can't provide that comprehensive, accurate map you'd need to navigate reliably.
So this really drives home the point. For a CUA to actually work in these environments, general vision models alone are just not going to cut it. You need specialized training.
Precisely. The specialized parsers they tested, which were trained for this kind of task, did much better. They hit F1 scores over 0.40 and had good localization. It confirms that task-specific training, probably using data like GUI-360 degrees, is essential for handling these dense, heterogeneous layouts.
Okay, so we see this clear divide. General models struggle, specialized models do better, but only if trained for this specific, messy desktop world.
Yep, that's the pattern.
All right, now let's pivot to the main event, action prediction, deciding the exact next step. And here, they looked at two really critical scenarios, relying only on vision versus using vision plus that accessibility data.
Yes, the visual-only setting versus the visual plus 11Y setting. And the difference is stark.
How bad was visual only?
Pretty much a disaster. GPT-4o, for example, only achieved about 3.12% step success accuracy.
3%?
Yeah. It just highlights how incredibly difficult, maybe even impossible it is to reliably figure out the precise action and where to perform it just from pixels alone in these complicated UIs.
Cool.
Too much ambiguity.
So the pixels aren't enough.
Yeah.
But adding the structured info, the accessibility data, or A11Y data, as it's often called, that made a difference.
A huge difference. Just to clarify for listeners, when we say A11Y or accessibility data, we mean that hidden structured information about UI elements, their role, button, menu, name, position, that Windows itself often provides.
Right, the stuff screen readers use.
Yeah, exactly. And providing this to the models was a game changer. GPT-4's success rate jumped from that dismal 3% all the way up to nearly 37%.
Wow, over a 10x improvement.
Yep. And GPT 4.1 went even higher, close to 40%. It's clear proof that these structured cues dramatically reduce the burden of visual reasoning needed for precise interaction.
Okay, but even with that massive jump, getting it right only 40% of the time, that's still a long way from being reliable enough for a real product, right? You wouldn't want an assistant that fails more often than it succeeds.
Absolutely not. 40% is much better than 3%, but it's nowhere near production ready.
So let's get to the core of why it's still failing, even with both vision and the A11Y data. The error analysis must be revealing here.
It is. If you look at the detailed breakdown of errors, especially for the models that were fine-tuned on GUI 360 degrees, the picture becomes very clear. They get pretty good at function prediction.
Meaning they know what kind of action to take.
Exactly. Click, type, drag. They predict the correct function over 84% of the time after fine-tuning. They know they need to click something or type somewhere.
Okay, 84% accuracy on what to do. That sounds pretty good. So where's the failure?
The failure is in the argument match accuracy. It lags way behind.
The argument, meaning where to click or what to type.
Precisely. So the model knows it needs to click with 84% accuracy, but it only identifies the correct element to click, the correct argument for that click function, about 25% of the time, even with fine-tuning and 11Y data.
Hold on. 84% accuracy on knowing what to do, but only 25% accuracy on where to do it. That huge gap, that really defines the problem, doesn't it?
It absolutely does. Argument mismatch error is the dominant failure mode by far. The model knows it needs to click the bold button, but maybe clicks the italic button right next to it, or it selects the wrong cell range in Excel.
Wow.
So this is the key bottleneck. It raises the critical question. Why is identifying the precise target element in the argument still so incredibly hard, even when the model knows the right function, and even when it has the structural hints from the A11Y data?
It suggests that even with the boost from A11Y, the combination of visual understanding and structural mapping still isn't precise or robust enough for the kind of sequential, high-stakes actions needed in these desktop apps.
Exactly. The sheer variability, the dynamic nature of desktop UIs, the nested menus, the unpredictable layouts. It seems current SOTA models, even fine-tuned ones, still struggle to consistently pinpoint the exact right target in that complexity.
So wrapping this up, what does this all mean? It feels like GUI 360 degrees isn't just another data set. It's establishing a much-needed high-bar benchmark.
I think that's right. It confirms that our current best models, even the big proprietary ones, are definitely not generalist computer users yet, not by a long shot. They need specific training data, like this dataset provides, and they heavily rely on structural hints like accessibility data to even function semi-reliably on the desktop.
And
Even then, fine-tuning delivers huge gains compared to out-of-the-box, pushing performance past trivial levels. But the end-to-end action prediction results, hovering around 40% success even with the 11Y data, show we're still far from human-level reliability. The paper really pinpoints the problem. Solving the precision challenge in argument grounding is key to the future of usable CUAs.
So the research clearly lays out the baseline and shines a spotlight directly on that remaining gap, the argument mismatch, the where problem. But there's a potential silver lining here, right? You mentioned the dataset includes failure cases.
Yes, and this could be crucial. GUI 360 degrees includes over 62,000 trajectories that failed, explicit examples of the agent getting it wrong.
Okay, so here's the final thought for you listening. We know argument grounding, finding the exact target, is the main hurdle. We know these models only get it right about 25% of the time, even after fine-tuning. What role could these 62,000 detailed failure examples play if future work uses reinforcement learning, feeding these failure signals back into the training loop? Could that be the key to finally achieving the kind of sub-pixel precision needed to bridge that gap from 25% to something truly robust? That feels like the multi-million-dollar question for the next generation of AI office assistants.